There's a glass jar sitting in a workshop in rural Ohio that has been producing electricity since before your parents were born. No lithium, no rare earth metals, no charger, just salt, water, and 2 pieces of scrap metal. The man who maintains it has never bought a replacement battery for that circuit in his entire life. The total cost of building it was somewhere around $6. That was in 1947. I know how that sounds. But stay with me, because what I am about to show you is not a trick, not a theory, and not something that requires special tools or a science degree. It is a working technology that was quietly shelved, not because it failed, but because it worked too well for anyone to build a business selling it twice. Let's start with the problem, because you already know it, even if you have never put it into words. Batteries die. They always die. Your phone battery starts losing capacity within 18 months of the day you buy it. The lithium pack in your cordless drill will be dead in 4 to 5 years, no matter how carefully you treat it. Even your car battery, which costs anywhere from $150 to $300, has a lifespan of roughly 3 to 5 years before it leaves you stranded. And here's the part that should make you angry. None of this is accidental. The average American household spends between $500 and $800 every single year on batteries and battery-powered replacements. That is a stream of spending that somebody, somewhere, depends on you maintaining forever. The moment you stop needing replacements, the revenue model collapses. So the incentive has never been to build something that lasts. The incentive has always been to build something that works just long enough to keep you coming back. But what if the long-lasting version already existed? What if it was invented, tested, documented, and then quietly pushed to the margins? Not because the technology was flawed, but because the economics of it were incompatible with a world built on repeat purchases. Here is where the story gets interesting. Back in the late 1800s, before the modern battery industry existed, there was a thriving category of technology called wet cells. These were open containers, jars, crocks, ceramic pots, filled with a liquid electrolyte and fitted with 2 different metal electrodes. They powered telegraph networks. They ran the first electric doorbells. They kept railroad signal systems alive across thousands of miles of track. Every farmhouse in rural America that had any electrical device at all before the grid arrived was running it off some version of a wet cell. The technology was not exotic. It was ordinary. It was the kind of thing a competent farm mechanic could build from hardware store materials and keep running indefinitely with nothing more than a periodic top-off of water. Then something shifted. Around the early 20th century, the push for portable, sealed, maintenance-free batteries began in earnest, driven partly by consumer convenience, but more significantly by the fact that a sealed, non-refillable battery creates a guaranteed replacement cycle. The moment the battery dies, the consumer has no choice but to buy another one. A wet cell that you can refill and maintain yourself for decades does not create that cycle. It creates independence. And independence, from a business standpoint, is a problem. Thomas Edison actually understood this. His nickel-iron battery, patented in 1901, was designed from the ground up to last. He wanted to build something a customer would buy once and never have to replace in their lifetime. And he largely succeeded. Documented examples of Edison batteries from the early 1900s were still holding usable charges in the 1980s. But by 1972, the last domestic production line for Edison-style cells had been quietly shut down. The public explanation was that they were inefficient. The real issue was simpler than that. A product customers buy once and maintain forever does not generate the kind of revenue that keeps shareholders happy. The communities that never connected to the commercial grid never gave up on wet cell technology. They kept using it, refining it, and passing the knowledge down through families. Over generations, through trial and error across many cold winters and hot summers, certain combinations of materials and certain ratios of ingredients emerged that produced cells of remarkable longevity. The chemistry they landed on was not complicated, but the specific variables they got right. The exact metals, the exact electrolyte concentration, the specific additives that prevent long-term degradation, those details are what separate a battery that lasts 6 weeks from one that lasts 60 years. Here's the science behind why it works, and I promise this will make sense without a chemistry textbook. When you place 2 different metals into a saltwater solution, you create a voltage difference between them. This happens because different metals have different tendencies to release electrons. The more reactive metal gives up electrons. The less reactive metal accepts them. The salt water acts as a conductor that allows ions to move between the 2 metals, completing the circuit. The specific combination that produces reliable long-term performance is galvanized steel paired with solid copper in a dilute saltwater solution. The galvanized coating on the steel provides zinc, which is the reactive metal that does the work. The copper is the collector. The critical variable most people get wrong when they try to replicate this at home is the salt concentration. Too much salt actually accelerates corrosion and kills the cell prematurely. The correct ratio is approximately 1 teaspoon of plain rock salt per cup of water. That is it. Not a tablespoon, not a handful. 1 teaspoon per cup. There are 2 additional ingredients that the long-running versions of these cells use, and both of them matter significantly. The first is a small amount of plain white vinegar, about 1 teaspoon per quart jar. The mild acid in vinegar lowers the pH of the electrolyte slightly, which dramatically slows the formation of metallic crystals between the electrodes. Those crystals, called dendrites, are the hidden killer of most homemade battery experiments. They grow slowly over months and eventually bridge the gap between the two metals, short-circuiting the cell from the inside. Vinegar interrupts that process. One cell that accidentally received pickling brine during its assembly reportedly outlasted the identically constructed cells around it by a factor of 3. That single observation led to vinegar becoming a standard part of the recipe. The second additive is oak ash, specifically fine ash sifted from burned dry oak wood, half a tablespoon per quart jar, added at assembly time and allowed to settle before the cell is put to work. Oak ash contains potassium carbonate, which functions as a natural electrolyte buffer. It improves the conductivity of the salt water without making it corrosive, and it stabilizes the chemistry of the cell under temperature fluctuations. Cells assembled with oak ash as part of the electrolyte mixture have shown measurably higher stable voltage output, roughly 10 to 15% higher than cells without it, and substantially longer operational lifespans. The industrial researchers who dismissed saltwater cells as marginal performers in the 1930s were testing cells without this ingredient. They were, in effect, testing an incomplete recipe and drawing conclusions about the whole concept based on a version that was missing a key component. Now let's talk about how to actually build one, because this is the part that matters most. Here at Hidden Fix Lab, we only share things that ordinary people can actually do. Start by picking up 6 quart-sized mason jars with metal lids, around $12 at any hardware store or big box retailer. You will need a 4-foot length of solid copper bar, the kind sold for electrical grounding applications, about $8. Pick up a 2-foot by 2-foot sheet of 24-gauge galvanized steel, which runs about $6. A 1-pound bag of plain rock salt, the kind sold for water softeners or ice cream makers, costs around $3. A 25-foot roll of 18-gauge insulated copper wire rounds out the list at about $5. Your total is somewhere around $34 for a 6-cell bank. Cut the galvanized steel into 6 rectangles, each about 3 inches wide and 5 inches tall. Cut the copper bar into 6 matching pieces. Drill a small hole near the top edge of each piece of metal so you can thread a short section of wire through it as a hanger. Prepare your electrolyte. Distilled water or clean rainwater works best. Tap water can work but introduces variables. Mix your salt at 1 teaspoon per cup of water, then add 1 teaspoon of plain white vinegar per quart. Optionally, burn a few lengths of dry oak wood, collect the fine gray ash, sift it through cheesecloth to remove coarse particles, and add about half a tablespoon per jar. Fill each jar about 3/4 full. Hang 1 galvanized steel strip and 1 copper strip inside each jar, suspended from the lid by their wires, positioned so they face each other with a gap of at least 1.5 inches between them. This gap is critical. If the metals touch, the cell short circuits instantly. Close the lids with the wires passing through small holes or notches you have made. Wire the 6 jars in series by connecting the zinc electrode in jar 1 to the copper electrode in jar 2, and so on down the line. Series wiring adds the voltages together. Check your output across the full bank with a multimeter. You should see somewhere between 5 and 6 volts. That is enough to run LED lighting, charge small electronics through a USB step-up converter, power a radio, or run a small fan. Now, a few honest limitations, because credibility matters more than hype. These cells produce low current. They are not suitable for running motors, appliances, or anything that draws significant power. They are emergency and supplemental power sources, not grid replacements. The electrodes will corrode slowly over time. This is normal and expected. A light scraping every 6 to 12 months keeps them performing well. Full electrode replacement becomes necessary every few years, and at hardware store prices, that costs almost nothing. Keep the bank in a ventilated space. Electrochemical reactions produce small amounts of hydrogen gas during operation, which is negligible in 1 or 2 jars, but worth accounting for in a larger bank. High ceilings, open shelving in a garage or outbuilding, or a basement with a window cracked, any of these work fine. Treat it with the same basic common sense you would apply to any chemical process in your home, and it is completely safe. One more note on temperature. These cells perform best when kept cool. Underground or partially buried storage, the kind of setup that maintains a stable temperature around 50 to 55 degrees Fahrenheit, significantly extends the life of the electrodes and the electrolyte. If you have a basement that stays cool year-round, that is your ideal location. What strikes me most about all of this is not the chemistry. The chemistry is simple. What strikes me is the durability of the knowledge itself. There are documented accounts of cells like these built in the late 1940s that were still generating measurable voltage decades later. not because their builders were geniuses, but because they got the variables right, maintained them faithfully, and passed the recipe down without letting it get buried under the next wave of consumer products. Here at Hidden Fix Lab, that is exactly the kind of knowledge we dig for, not because the modern world has nothing to offer, it does, but because the older solutions are often simpler, cheaper, and more durable than anything on the shelf at a box store. The saltwater cell did not get replaced because something better came along for most household applications. It got replaced because something more profitable came along. Those are not the same thing, and once you see the difference, you start to look at a lot of things differently. You do not need to go off-grid. You do not need to make any dramatic changes to your life. You just need a shelf in your basement, $34, and one Saturday afternoon. What you build that afternoon could still be running when your kids are grown. That is not a sales pitch. That is just what happens when you get the chemistry right and stop expecting things to fail on a schedule somebody else set.